So this is the answer key to the review that was posted. So let's compare a Bronsted-Lowry acid and an Arrhenius acid. Arrhenius acid is an acid that creates or gives off H plus ions in aqueous solutions. So the key here when differentiating acids is the aqueous solutions, right? So Arrhenius only considered acids to work in aqueous solutions, and therefore like an HCl gas would not be considered an acid. However, Bronsted-Lowry said that an acid is anything that donates H plus ions. So that could be to water, like Arrhenius acids, or it could be to bases like ammonia to form ammonium ions. So this included the general case of neutralization reactions, and HCl gas was considered an acid. So donates H plus ions, and that's it. So that's the Bronsted-Lowry definition of an acid. So state the Bronsted-Lowry acids. They would be acetic acid, and H3O plus is also a Bronsted-Lowry acid because it also can donate an H plus to solution. Technically, H2O could also be considered a Bronsted-Lowry acid, but not in this scenario because H2O is acting as a base. So state one acid-base conjugate pair. This would be the acid. This would be the conjugate base, or you could do, base to conjugate acid. Either one is good. What's the difference between a strong acid and a weak acid? There should be a decimal point here. 0.1 molar. How lazy am I to go fix that? I'm probably too lazy. I'll just fix it later. What is the difference between a strong acid and a weak acid? A strong acid is an acid that completely dissociates in solution. Weak acid only partially dissociates in solution. So if you had the same concentration of a strong acid and a weak acid, the strong acid, the H3O plus concentration would be 0.1 molar exactly. For the weak acid, depending on what it is, the H3O plus concentration would be somewhere under 0.1, definitely. It would probably be somewhere around, I'm just putting out a number here, 1.34 times 10 to the negative 3. This is for 0.1 molar acetic acid, right? So our pH for this strong acid would be lower because it has a higher H plus concentration. So acidic, basic, or neutral salts. So we have this and then Cl minus. Again, you can think of it as two different ways. Did I make a mistake again? Yeah, I think this is supposed to be an NH4. Where did I get these questions from? Interesting. Okay, I will have to go fix this now. Okay, hold up a second. Okay, I fixed that on the hub, and so therefore this should be this salt, and you can kind of tell that this came from CH3NH3 plus HCl, and therefore this was a strong acid weak base combination which resulted in an acidic salt. We can also tell because this ions, if you add this to water, there's no reaction. But if you add this to water, you're going to get an acid because it's going to donate that H plus to water. So you're going to get an acidic salt over there. KCl, again, comes from KOH plus HCl. strong base, strong acid, neutral salt. Again, K plus and Cl minus both don't react with water because they're both conjugates of strong bases and conjugates of strong acids. So that's that. Determine pH of 5.75 times 10 to the power negative 5 molar KOH solution. So we know our OH concentration for a strong base is the same as this is completely dissociating. So our pOH is negative log of this answer, which is 4.24. So our pH will be 14 minus that answer, which is 9.76. 3 sig fig, so technically it should be 760. Okay. That was easy-ish, hopefully. pH of CH3NH2. So we're gonna do a ice table. Oh, you know what? Never mind. The thing before was right. It was supposed to be. I'm just sleeping. It's NH3 plus, not NH4 plus. Because this is too many bonds now. Because we have 1, 2, 3, 4, 5. Yep. I just corrected it for nothing. I should have trusted myself. Okay. We have to go back and fix that. But this is NH3 plus and Cl minus. It came from NH2 plus HCl, which gave us that. So, yes, that makes sense. So this is not an NH4, it's just an NH3. It doesn't change the answer, it's still acidic, it's just the matter of the 3-4 thing. So we will continue, and I will re-update it on the hub. Save. Go back to the hub and re-upload this guy. There. Okay, we were back to methylamine. There we go. Whatever this is called. This is a base, so it's gonna accept a proton from water, accept a hydrogen, and without its electron from water, become NH3 plus, and you have OH minus. So here the concentration was 0.05, 0 minus X plus X plus X, 0.05 minus X, Ka, or Kb rather, of this can be obtained from the chart at the very end. So CH3NH2. This is acids, bases. CH3NH2, 4.6 times 10 to the power negative 4. There is another problem. This does not exceed 500. And so therefore we are going to make another change to this question. We're going to change this value to 0.5 instead of 0.05. My bad. Okay, so we're going to do initial concentration divided by Kb is greater than 500, justified. And I will always give you a question that is justified. This was a slight oversight. If you had done it with the justification, that's fine. It's technically over 100, so it just depends on how accurate you want to be with your answer. If you do the justification and say over 100, I will accept that. So KB here, I can cancel off this negative x, is x squared divided by 0.5. And so I take my KB value, 4.6 times 10 to the negative 4, times that by 0.5, take the square root. I get x equals 0.0151657 something. Take the negative log of that to get my POH, 1.819. So my pH will be 14 minus that answer, which is 12.1808. So that well, I've given you, let's assume I wrote 0.500. So it's 3 sig figs. So 1, 2, 1. Sig, yeah, there we go. That should be good. I have to go back and change this again. It goes to show you learn a lot when you write your own tests or reviews or whatever. Okay, so this is a salt, HCOOK. So this was made up of HCOO minus and K plus. This does not react with water because if it did, it would form KOH, which is a strong base. So the reaction equilibrium lies all the way to the left with the ion, so that's basically no reaction. And what we're going to do is just have HCOO minus reacting with H2O to form formic acid plus H3O plus, no, OH minus. There, and this is 0.25. Yeah, water's gone. 0, 0, minus x plus x plus x. 0.25 minus x, x, x. And then now there's an extra step here because this is a salt. We are given at the back. We are given our pH for pKa for formic acid. Is this guy 1.8 times 10 to the negative 4. So here we do Ka of formic acid is 1.8 times 10 to the negative 4. Therefore Kb of formate ion will be Kw divided by the Ka, which is 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 4, which is 5.5 bar times 10 to the negative 11, which we will now use to be equal to x squared divided by 0.25. Of course, I still have to do my 0.25 divided by Kb is greater than 500, therefore justified. So I can get rid of this minus x. So multiply this answer by, the Kb by 0.25, take the square root. X equals 3.726 times 10 to the negative 6. OH minus concentration is negative log of that. 5.4286. pH is 14 minus that. Whoops. .571. That's my answer. Determine the pH at equivalence. Okay, so this is a equivalence point question. So this is gonna be a bit of calculation. So we have to find. Okay, so let's do. First, we have to write our neutralization reaction. So acetic acid is reacting with sodium hydroxide, which will give us our salt plus water. Now, I know my 0.200 moles per liter here. I know this is 0.800 moles per liter. My volume here is 0.1 liters. So again, you can I know at equivalence point, my number of moles of acid equals number of moles of base. So the concentration times volume of acid equals the concentration times the volume of base, which I can now find to be 0.8 times 0.1 divided by 0.2, which is 0.4 liters. Okay, and then again, I want to find my concentration of this, so concentration of my salt, because that's what's going to contribute to my pH, because these guys are completely canceled each other out. So my concentration of salt is going to be number of moles of either one, because both of them are the limiting reagent. They both exactly cancel each other out. So I'm going to do 0.8 times 0.1 number of moles. You can do 0.2 times 0.4, and as you'll see, you should get the same answer. But I do have to do a dilution step because I am adding two solutions together. So my concentration is going to be that number of moles, which was 0.08, divided by 0.5 liters, which gives me 0.16 moles per liter. So this is my concentration of my salt. Again, the salt is Na plus and acetate minus. The Na plus doesn't matter because it reacts. It is a super weak acid, and therefore does not react at all with water. So we're gonna basically focus on this guy. I don't know why just all of them turned out to be bases. Maybe I should have switched one up and given you an acid. Too late. 0.1600 minus x plus x plus x. 0.16 minus x, x, x. And therefore, again, now to find this is just like a basic salt, exactly the same thing we did. Ka of acetic acid is 1.8 times 10 to the negative 5. Kb of acetate will be Kw divided by Ka, which is 1 times 10 to the negative 14 divided by this, which is 5.5 times 10 to the negative 10. I also do 0.16 divided by Kb greater than 500 justified to cancel out this negative x. So I do 5.5 times 10 to the negative 10 equals x squared divided by 0.16. So I'm going to do my Kb times 0.16 square root x equals, which is OH minus concentration basically, equals 9.428 times 10 to the negative 6. Take the negative log of that answer. POH, 5.025. pH is 14 minus POH. So pH is 8.97. And that is my answer. Compare the basic strength of the conjugate base of a strong acid and the conjugate base of a weak acid. So this is the conjugate base of a strong acid is supercubed weak. So super weak. Example, Cl minus, and you can say, does not react with water. The conjugate base of a weak acid is just regular weak, so it's not super weak, it's just regular weak in the same way. So for example, what's the conjugate base of a weak acid? Acetate ions. Does react with water and produce change in pH. Technically, the chloride ions probably do too, but to like such a negligible extent that we do not take into account. How are buffers made? State the importance of buffers in society. So buffers are made using a weak acid plus its conjugate basic salt, or a weak base plus its conjugate acidic salt. Either two. You can give one example. How are buffers used in society? You can explain how buffers are used, and you can even use the use of a buffer is to maintain pH levels. So the easiest example is in like scientific experiments, buffers are used to model systems that exist in nature. For example, like the blood, you can use a buffer to model that system and then figure out where enzymes work optimally, etc., etc. Technically, society might have been a bad word. I was looking, even if you'd said blood is a buffer, and that helps, make sure that all the enzymes carry out the reactions that they're supposed to, and to make sure that the pH doesn't change too much to affect those enzyme reactions, that would have been fine as well. Draw a titration curve for a strong acid, weak base. The solution starts off with a weak base. Strong acid is added drop by drop. So it looks something like this. Here would be the buffer region. And you know that the equivalence point will be acidic. So estimate the pH. Literally any pH between like 1 and 7 is correct. I would say like 5.5 or 5 would be appropriate. Closer to 1, that's kind of getting unrealistic. Closer to 7, that's also getting unrealistic. So somewhere ideally between 3 and 6 would be the range I was looking for. But technically, as long as you said it was an acidic equivalence point, I would give you the mark. Calcium fluoride, I think this is right from the textbook. Squared, very important here. Salt A has a KSP of that, salt B has a KSP of that. Salt A has higher KSP, therefore it also has higher solubility, because KSP gives you the solubility product constant, or how soluble these salts are in water. It correlates directly to your molar solubility. Okay, so this is just a molar solubility question. Silver chromate, you're going to do the dissociation of that 2Ag plus CrO4 minus KSP is given, so this is a solid, so you basically don't need this. 0, 0 plus 2x, x, 2x, x. So 2x the whole squared times x equals KSP. That's our expression. This is 4x squared times x, so 4x cubed equals 1.1 times 10 to the negative 12. So you do 1.1 times 10 to the negative 12 divided by 4. Take the cube root of that answer, and you get x equals 6.503 times 10 to the negative 5, and that is my molar solubility of silver chromate. Okay, I just did a whole bunch of these questions, but depending on whether you watch the other videos, you may or may not have. But this is a will the precipitate form kind of classic-y question. So we have our barium nitrate plus sodium fluoride, and I have 0.2 liters, 2 times 10 to the negative 3, 0.05. Those are my values, and again I'm going to form here barium fluoride plus sodium nitrate, and I know this is the solid, just because all nitrates are soluble. And if you look at the KSP chart, it's on the next page. Barium fluoride is listed. Let's look at the KSP. Barium fluoride 1.84 times 10 to the negative 7 right there. So I'm just going to write my dissociation expression. And I forgot my KSP. I think it was 1.84 times 10 to the negative 7. Fairly certain. Okay, now again, to calculate our QSP, we need a concentration of barium ions and fluoride ions, and therefore we get that from here. Concentration of barium ions is equal to the concentration of barium nitrate, because that's a 1:1 ratio. 0.2 times 2. So again, concentration times volume divided by total volume, which is 0.200 plus 0.05, right? 0.25. I'm going to do that calculation. And it gives me a concentration of 1.6 times 10 to the negative 3. Excellent. Fluoride ions is equal to concentration of sodium fluoride is equal to 0.05 times 0.0002 divided by the same total volume. Is that 2? Yeah, that's 2. Excuse me. Concentration of, wow, that's tiny, 4 times 10 to the negative 5. So let's put these values into our initial concentrations here. 1.6 times 10 to the negative 3, 4 times 10 to the negative 5. My QSP is calculated by doing barium concentration times fluoride concentration squared, which is 1.6 times 10 to the negative 3, 2.56 times 10 to the negative 12, which is in fact lesser than my KSP, so no precipitate will form because these numbers over here are not big enough. So any solid that tries to form will instantly move towards the right hand side of the reaction to reach equilibrium, and therefore no precipitate will form because the ions you need more ions basically, not more solid. And that brings an end, I think, to our review. These are going to be the basic kinds of questions. We'll do some theory review, I think, in class on a review day, which at this point I still don't know when it is because I'm not sure if we should do it on Tuesday, if Wednesday is a day off, but I don't know if Wednesday is a day off yet, so we'll see. It's going to be fun times. See everybody in class.